Okay, hello to nobody because I'm talking to myself right now. This is a fake lecture. This is an optional lecture for 32H about something called the implicit function theorem, which, because we're in the quarter system, we don't have much time to talk about fun things like this. So this is a bonus lecture. Even though I'm talking to myself, I'm going to pretend like I'm giving a regular lecture just because. Okay. So what is the implicit function theorem? Well, we've talked about the inverse function theorem. It turns out that the implicit function theorem is equivalent. It's a different theorem, says something slightly different, slightly more complicated too, but it's equivalent to the inverse function theorem. Therefore, it's just as important. And in some sense, I would say it's kind of more important just because the statement is more applicable. Okay, because the statement of the implicit function theorem is pretty complicated, we're going to have a big buildup. I need to give you some motivation. So I want to start off with a very simple motivating question. This is to consider the equation x squared plus y squared equals 1. My question, which is a question that we've thought about for a long time in math, way back to high school or middle school or whatever, can you solve for y as a function of x? Easy question, right? Does anyone have any ideas? Okay, so Joe has an answer. Thank you, Joe. Joe says, well, sure. Just do the algebra. If you want to solve for y in terms of x, move the x squared over, take a square root, and you get something like this. So thank you for the answer, but it was not a very good answer. Does anyone else have ideas? Okay, thank you, Gauss. Gauss has another idea, which is no, when you take a square root, you have to consider both the positive and negative square root, right? So when you do the algebra, you actually get y equals plus or minus the square root of 1 minus x squared. And that's not a function because it doesn't pass the vertical line test. Okay, so thank you, Gauss. There's a better answer, but actually it's still not the correct answer, in my opinion. Gauss was pretty smart, but, you know, he's pretty old now. The real answer is that this question wasn't very good. The real answer is I need to do a better job of asking this question. So let me try again. Okay, so the more precise question is as follows. Fix a point on the circle. Let me draw a picture to accompany this. So we have x and y, and then we have this equation x squared plus y squared, which cuts out some circle, radius 1. And here's what I actually want to ask. Pick a point on the circle, any point. So fix x naught, y naught on the circle x squared plus y squared equals 1. Let me draw a point in here. What I really want to ask is the following. Is there an open ball around x naught in R? Such that, so first of all, what do I mean by that? At this point, I could drop down to my x coordinate here. So this is the value x naught. And what I'm looking for right now is I'm looking for some open ball in the x-axis that contains this point, such that the points on the circle near this fixed point can be described as a function y in terms of x on this ball. So let me write that out. So is there an open ball around x such that y is a function of x on this ball near, and this is kind of the key part, near this fixed point? As Gauss showed us up here, in general, the answer is no, that I cannot solve for every point here, y in terms of a function of x, just because this curve fails the vertical line test. It cannot globally be a function. So what I'm actually interested in is, given a fixed point, can I describe the curve nearby as a function of x, as the graph of a function of x? This is the actual question that I'm interested in right now. And I think I already spoiled the answer, but the real answer is, well, it depends. So let's think about this. Maybe I'll say the answer is it depends. For example, let's consider this exact situation that I drew up here, where the y-coordinate of my fixed point is positive. So I could say, there's a couple cases we can consider. One of them is that I have a point on the circle where my y-coordinate is positive. That's basically exactly this picture that I drew here, so let me copy it. In this case, the answer is yes. If y is positive, then, again, I won't do this formally. We'll think about this later formally, but if y is positive, then yeah, it seems like, well, necessarily if y is positive, the x value is going to be something like this, and then I can find some ball. And then if y is positive, this first answer that Joe gave us, this is correct, right? If y is positive, y will be the positive square root of 1 minus x squared. So in this case, since y is positive nearby my fixed point, I can actually solve for y as a function of x. And again, it's important that I'm really only restricting the domain of my function here to be some ball, some small ball potentially around x naught. Okay, well, another case is, what if y is negative? So the picture here would be almost the same. I have my circle, but this time I pick a point on my circle where the y-coordinate is negative. So here's x naught, y naught. Well, I basically just do the same thing that I did before. I look at whatever my x-coordinate is, and because y is strictly negative, I can find some little open neighborhood of this point x naught such that the curve nearby my point x naught, y naught is described as the graph of a function. And in this case, so the answer is yes again. Since y is negative near y naught, when I solve for y in terms of x, I'm going to get the negative square root instead of the positive square root. And again, I'm not saying globally or anything like that. I'm just saying in a small neighborhood of x naught, the y values on the curve are described this way. So on a small ball, around x naught. Okay, so we've considered the case when y is positive, we've considered the case when y is negative. There's one remaining case, which is actually just 2 points on the circle, right? It's when the y value of my fixed point is 0, here and here. So there's 2 points that we have not considered. The case when y not equals 0, which, you know, on the unit circle is explicitly at the points plus or minus 1, 0. I claim that the answer is no here. Let's think about this. So answer this time is no. If I draw my picture again, the point I've picked is, say, right here. Well, maybe let's consider the point 1, 0 for the moment. What am I trying to do? I'm trying to solve for y as a function of x nearby x, nearby the given value of x naught, which in our case is 1. In other words, I want to look at some neighborhood of this point. For example, in the other two examples, or the other two cases we looked at, what I'm really asking is I go to this point on my curve and I look in a little neighborhood of that point and I ask, can I write this as the graph of a function? Here I looked at this little neighborhood. Can I write this little chunk of the curve as the graph of a function? In this case, if I look at some neighborhood of my point, any neighborhood I look at that contains this point, it's going to fail the vertical line test, right? So any chunk of the curve containing the point 1, 0. And like I said, because I want a neighborhood of my point, I do want to consider, I have to consider necessarily both above and below the axis, which is the point here. So any chunk of this circle will fail the vertical line test. So the answer is no. You cannot solve, even locally, for y as a function of x nearby this point. Okay. This is the situation that the implicit function theorem tries to understand. You know, in this situation with this specific example, we were able to draw pictures and just think about it geometrically by saying, oh yeah, here you'll pass the vertical line test, here you will, here you won't. But in general, that's not a good way to go about things. So we want some mathematical tool to be able to tell us in general, when can I locally solve for some variables in terms of other variables? Now, let's see. To kind of motivate the statement of the implicit function theorem, here's what I want to observe next. And this is kind of the key observation. This equation that we're working with, x squared plus y squared equals 1, this is a level curve of a function, right? I'll say it's a level set of the function from R2 to R, I'll call it G, where G is x squared plus y squared. What we're going to do is we're going to take the Jacobian of G. We're going to see if we can answer this question more systematically about locally solving for some variables in terms of the other using the Jacobian of this function. So note that I can find the Jacobian. What do I get? Well, it's going to be a 1 by 2 matrix. The first component is going to be the x derivative of g, which is 2x. Second component will be the y derivative, which is 2y. Okay. Not the most thrilling computation, but here's the point. So we had 3 different cases, right? One of the cases was when y was positive, one of them was when y was negative, and the other one was when y equals 0. So when y was positive, so this was case 1, actually let me write it like this. So the answer was yes, we can solve for y in terms of x. Exactly when y naught was non-zero. So my Jacobian at that point would look like 2x naught, 2y naught. And basically what we found is that we can solve for y in terms of x near this point when this number is non-zero. The answer was no when y was 0, for example, at the points plus or minus 1 comma 0, in which case the Jacobian at that point is plus or minus 2 and then 0. Here, this number is 0. Okay, so this seems a little silly. Like, what are we doing? Basically, the point in this specific example is we were looking at somehow tangent lines at different points on the circle. So let's see. In the first example, the tangent line would kind of look like this, sort of. And that tangent line, that looks like a function. That looks like the graph of a function, right? Y in terms of x. Likewise, down here, yeah, there it looks like the graph of a function too. Looks like we can write y in terms of x. But here, there's like a vertical tangency. That tangent line fails the vertical line test. So since the tangent line cannot be written as a function of y in terms of x, you can't do it locally to g. That's sort of what this is measuring. When this second number is non-zero, that's indicating that the tangent line can be solved as the graph of a function y in terms of x. And when this number is 0, we have some vertical tangency. Turns out that the generalization that we're going to look for in the implicit function theorem is that when this, so I'll say it this way. So what we really want to be thinking about is when this matrix, so this is a 1 by 1 matrix, which is a number, but it's a matrix. When this matrix is invertible, the answer is yes. When it's not invertible, the answer is no. That's what we're heading towards. Now I need to build up some notation in order to state the theorem precisely, but this is what we're working towards. Okay, so here's the setup. So in the previous example, we had 2 variables, x and y, and I was curious if I could solve for x or for y in terms of x. maybe just for some clarity, for some reason, I'm going to switch my variables to y and z. I don't really know why. I made this decision when I was typing up notes, and so I guess we're going to use y and z. So earlier I asked the question about x squared plus y squared equals 1. I'm going to switch my notation a little bit, and I'm actually going to ask this about y squared plus z squared equals 1. So they're just letters, right? Don't mean anything. But so now my question is going to be, can I solve for z as a function of y? Now, in general, here's what I'm actually interested in. Suppose I have a bunch of y variables and a bunch of z variables. So suppose we have variables y1 through yr. So little r is some number. I have r y variables. And I have k z variables. So here r would be 1, here k would be 1. In total, I have 2 variables. And in this general situation, in total, I'm going to have r plus k variables. Okay. Now, in the motivating example situation, we had 2 variables in one equation. More generally, I want to consider systems of equations. Like if I have a big system of equations of a bunch of variables satisfying certain relationships, I could ask, can I solve for some collection of those variables in terms of the other variables? So more generally, I have r plus k variables, and suppose I have a system of k equations. And I could write each of these equations as follows. G1 of all of my variables equals some number C1, where G1 is some function from r plus k to r. So that's my first equation, where G1, so this is going to be a function from, it eats r plus k variables, and it spits out a number. But I said that I have k equations, so I actually have k copies of this kind of thing. So I'll say da 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 da, and then here I have a function g all the way down to gk of all of my variables equals some number ck. And it's not that G1 is just a function from r plus k to r. It's that all of these things, each of these expressions are functions from r plus k variables to r. Okay, the first remark I'll make is that in this setup, it is really important that we have the same number of equations as we have z variables. Turns out that this is important. For example, this was the case in our motivating example. I had 2 total variables. I had 1 z variable and 1 equation. Okay, so it checks out. My question now is, so I'll write this imprecisely because I'm going to write a more precise version in a second. But given a system of equations like this, suppose I find one solution. Suppose I find a point on the solution set, like we found a certain point on the circle. The question is going to be, can I locally solve for the z variables in terms of the y variables? So imprecisely, the question we want to answer is, can we locally solve for the z variables as a function of the y variables? That's exactly what we did with the circle example. Now, to write down the more precise version of the question, I want to introduce some more compact notation, because with this business it gets really annoying writing out all of these variables. So here's some notation. First of all, I could consider the vector of just my y variables, of which I have r, not k. So if I only collect my y variables, I can think of this as an element in r, right? And the shorthand that I'm going to use for this vector is vector y. Okay. So if I write vector y, this just means the vector of all of the r variables, and this is an element of r. Likewise, probably not surprising, if I write vector z, this is just going to be the vector of z variables. This will be an element of rk. So the point then is that given an element of r plus k, I can write this as sort of a vector with two components, where each component is a vector, right? It's like the first r things, the y variables, followed by the z variables. So that'll make my life a lot easier. The next simplification that we can make is with these g functions. So I have I have k g functions. Each of these functions eats r plus k variables and spits out a number. And altogether, that gives me a system of equations. What I'm going to do is I'm going to write down a new function that I'll just call g, which uses all of these. In particular, I can think about each of these scalar valued functions as being the component functions to a vector valued function. Okay, let me write that down. So I'll define g. This is going to be a function from r plus k, so Euclidean space of dimension little r plus k, to rk by, well, g eats in r plus k variables, So the input of g is vector y, vector z. And the thing that it spits out is the k vector consisting of all of these component functions. So the components of g are going to be g1 of yz, all the way down to gk of yz. And indeed, this is going to be an element of Rk. Okay. Oh, and then I can do the same thing. Sorry, I'm going to scroll back up to my system of equations again. On the right here, I have k constants. Right, I have C1 through Ck. I can collect those into a vector, and I'll write vector C. This is just the vector C1 through Ck. So vector C will be an element of Rk. Okay, so with all this notation, this is going to make writing a lot of this stuff a lot easier. But it can be kind of intimidating at first, and it might take a little while for things to really click, or for you to get used to thinking about all of this stuff with more abstract notation. But I'll repeat, vector y is just the vector of all the y variables, vector z likewise, and g, plain old g, this is a function from r plus k to k, whose components comprise of the k equations from above. Okay, with all of that, with all of this new notation, here is the question that we want to answer using the implicit function theorem. So here's the precise question, which is a direct generalization of the first precise question that we did with the circle. Oh, right. So, sorry, let me back up. Let me remark that the point of this is that now we can rephrase this whole system of equations as g of vector y vector z equals vector c, right? This expression right here captures all of this data. It's just a more compact way to phrase a big system of equations. Okay. So now the precise question is, I'm going to fix a solution of that big system of equations. Let's suppose that we've found a solution. So fix such a point, now this is a point in r plus k, such that it satisfies that system of equations. In other words, g of this point equals vector c. What we want to ask is there a ball around y naught in, so y naught is an element of r, right? So I'm looking for a ball in r dimensional space around my point y naught such that we can solve for z as a function of y. So I'll say it this way, such that near this point, the values of z can be described as a function, that says function, I think, of y. Okay, in other words, to think about this a little bit more geometrically in relation to our circle example, can we describe the set of points Okay, I had some technical difficulties. My computer ran out of storage in the middle of filming this. Should be back in business now. Anyway, what I was describing is that this question geometrically we can phrase as follows. We have some system of equations, and this cuts out some surface or something. Think about it as being some hypersurface or some higher dimensional blob. Cuts out a blob. So can we describe the blob described by this system of equations as the graph of some function where phi eats y variables and spits out z variables? This is what we want to do, and this is the question that the implicit function theorem answers. And again, I'll reiterate, this is a complete direct generalization of this circle thing that we talked about. Okay, so I mentioned that it turns out that the answer is related to some sort of matrix inside the Jacobian being invertible. So what I want to do is introduce some more notation. Which is given a function g like this. So this is a function from r plus k to rk. Well, we could compute the Jacobian, right? So the Jacobian in our usual notation is going to be g prime of y comma z. And this will be a k by r plus k matrix. What I want to do, though, is I want to think about this as being a block matrix. So what I'm going to do is, so I have k rows in my matrix. I'm going to chop this up into two sub-matrices. One of those matrices will correspond to the first r columns, and the second one will correspond to the last k columns. So if I do that, if I only look at the first r columns, what am I doing? Well, I'm taking all of the derivatives of g only with respect to the y variables. So this like restriction of the Jacobian, I'm going to define it to be this notation. So by definition, when I write g prime sub y, I'm referring to the part of the Jacobian matrix of g corresponding to the first r columns. In other words, corresponding to all the derivatives only with respect to the y variables. Likewise, the last k columns the notation I will use to refer to this submatrix is, unsurprisingly, g prime sub z. Now let's do some dimension counting, just some sanity checks. So this matrix, it should have k rows and r columns. So this matrix is an element of m sub k by r. And likewise, this g prime z thing, this is an element of Well, it has k rows and k columns. Okay, so this thingy right here, G prime sub z, this is a square matrix. That's important. Okay, so all of this notation has been ridiculous, and this is a lot to absorb, and this is all kind of abstract. So let me really quickly just do a quick example to show you what all this notation means, and then we'll state the implicit function theorem. So quick example. Define G, let's see, what do I want to do? Let's have G go from R3 to R2 by G of, and the way I'm going to do this is I'm going to have one y variable, so little r is 1, and then two z variables. So that's 3 total variables, and then I need to spit out a 2 vector. And let's see, the first component could be y1 z1 squared plus z2, and the second component could be y1 squared minus z1 z2. In other words, this expression right here is G1 in our original notation. This expression right here is G2. Anyway, then we can compute the Jacobian. So G prime of y1, y2, y3. This is going to be a 2 by 3 matrix. The first row will be all the partials of this thing. So the y1 partial is going to be z1 squared. The y2 partial, oh, what am I doing? y1 and then z1, z2. Those are my variables. Sorry about that. So the y1 partial is z1 squared. The z1 partial is 2y1 z1. And the z2 partial is 1. Then I do the same thing for the second row. It's going to be all the derivatives of this thing. The y1 partial here is 2y1. The z1 partial is negative z2. And the z2 partial is negative z1. Okay, so in this case, this matrix right here, this is G prime sub y. It's the portion of the Jacobian only with respect to the y variables. So in this case, this is a 2 by 1 matrix. And this guy, this is G prime sub z. And again, it's a square matrix, corresponds to the derivatives of the k components with respect to the k z variables. Okay, so the question we're interested in is, can I locally solve for the z variables in terms of the y variables? I mentioned this at the beginning when we were talking about this circle example. So actually, now that we're back here, let me tie together the new notation with what we've done here. Now I'm using x and y, right? But I've switched to y and z. But this submatrix and this submatrix, this would be the G prime sub z guy. And I said that when this matrix is invertible, the answer is yes. When it's not invertible, the answer is no. So more generally, if you have a big system of equations with a bunch of variables, if the corresponding G prime sub Z matrix is invertible, the answer will be yes. Okay, so finally, I can actually tell you what the implicit function theorem says. So here's the theorem. This is the implicit function theorem. Okay, so the setup is, suppose that we have this function g. It's a function from r plus k to rk. And I need to assume that not only is this differentiable, but it turns out that you need the partial derivatives to all be continuous. So you need this to be C1, you need to be continuously differentiable. So suppose g is differentiable with continuous partials. This is just a technical assumption. I wouldn't worry about it too much for our purpose. Okay, so fix fix a vector c in the output. So this is our vector of constants. And fix a point y naught, z naught in r plus k, such that g of that point equals c. In other words, I've found one particular solution to my system of equations, or geometrically, I've found one point on my blob described by the system of equations. Okay, the punchline is if the submatrix G prime sub Z at the point y naught z naught, if this is invertible, remember this is a square matrix, it's k by k. If this is invertible, then the answer is yes. Then there is an open ball around y naught, which is just an element of R, and a differentiable function. So maybe I'll call my open ball U. So there's an open ball and a differentiable function phi. This is going to be a function from U, which is a subset of RR to RK, such that nearby this point, so I'll say such that nearby the point y naught z naught, whatever that means there's some open set around y naught z naught. I'm going to ignore those details for now. But so nearby our fixed point, the set of points yz satisfying this system of equations is the set of points yz of the form z equals phi of y. In other words, locally near the fixed solution point, the blob described by this system of equations is the graph of some function phi. Okay. There's a moreover part to this statement as well, which tells us about the derivative of phi. So moreover, phi prime at y naught, so this is the Jacobian at y naught, this is going to be a k by r matrix, and it turns out that the Jacobian is -1 times the inverse of this G prime Z matrix times the G prime Y matrix. Whew. Okay, this is the statement of the implicit function theorem. This is a big boy. It's kind of a lot to absorb here. But hopefully all of the preceding discussion about what we're doing clarifies what this says. Now, I still have a couple remarks about the statement, because there's a new part here that I haven't talked about. Once I can draw a straight line. There we go. The new part is this moreover statement about the derivative of phi. So why do I care about this thing, or why would it be useful? Here's the deal with the implicit function theorem, right? If you think about our circle example that we started with, y squared plus z squared equals 1, in that case, like let's suppose that we were at a point where we can solve for z as a function of y. In that case, you can actually do the algebra, right? Move the x, take square root. You can actually do the algebra to solve the equation. It's not hard. But very generally, suppose we're given like a super complicated system of equations. They could be highly nonlinear. In general, the algebra to actually solve the system of equations for some variables in terms of the other, it could be extremely difficult. So the implicit function theorem tells us that, if this matrix is invertible, it is theoretically possible to solve for z as a function of y. But it doesn't tell you how to do that, right? It doesn't tell you how to do the algebra to solve for z in terms of y. It just tells you that it's possible. So let me write this down as a remark. So the implicit function theorem tells us it's possible, it is possible, but it doesn't say anything about how to actually find this function phi, but doesn't say how. And again, that's to be expected because this is a highly nonlinear problem, potentially. But it does tell us about the derivatives of phi. So we can get a good degree 1 approximation using that Jacobian. But what we could do is, I'll say it this way. So, but phi of y, if it exists, again, I don't know what it is, but using this derivative, using this order 1 approximation, I could say, well, this is approximately going to be, I'll start at y0 plus the Jacobian at y0 times vector y minus vector y0. So this is the case for any differentiable function, right? You can get a good order 1 approximation of that function as follows. Now, oh, and I also guess I didn't write, let me squeeze this in. The other thing that phi needs to satisfy is that phi of y0 needs to be z0. That should make sense. So in a differentiable function phi such that and phi of y0 is z0. That's important. Anyway, so phi of y0 is z0. And then, according to this moreover statement, we know what the Jacobian of phi is. It's minus the inverse of g prime z times g prime y. And then I've got this h vector, y minus y naught. Okay, so this is really cool. Like I said, this is a lot of ridiculous notation, and it's kind of hard to keep track of what we're doing. We'll do some concrete examples in a second, but what this tells us is that, you know, the implicit theorem, the implicit function theorem gives us conditions on like when, yes, it is theoretically possible to solve for z in terms of y. Doesn't tell you how, but we can get a good local approximation. Here we have an expression that tells us basically the tangent whatever to our function phi. Anyway, like I said, we'll do some concrete examples to see this in action so you can see what I mean and why this is useful. But first, I want to give you the idea behind the proof. A full proof is pretty involved. I might do another video about that, we'll see. But I want to at least tell you the idea of the proof, because the idea is very nice. Okay, proof, idea. So again, not a formal proof. The idea uses the same philosophy as that of the inverse function theorem. So really quickly, let's think about the inverse function theorem again. The philosophy behind the inverse function theorem, and actually the philosophy behind anything in calculus, is that if you have some highly nonlinear problem, if you have some difficult curvy nonlinear problem, that's probably hard to solve. But if you go to a point, you can find a linear approximation to that problem. And if you can solve that, if you can solve the linear thing, then locally nearby your point, you can solve the nonlinear thing. In the case of the inverse function theorem, specifically, the problem was if I have a function, I want to know, is it invertible near some point? Well, what do? You ask, is the derivative invertible? And if the derivative is invertible, then locally, yes, the function's invertible. So again, the whole philosophy is I have a highly nonlinear problem, go to a point. If the linearized version of that problem is solvable, then locally the original problem is solvable. Okay, so what we're trying to do is I want to solve this equation for z in terms of y. I'll just say for z near my given point y naught z naught. G is probably nonlinear, probably has some crazy equations, don't know what to do. So what I'm going to do is instead of trying to solve the nonlinear problem, I'm going to linearize. I'm going to consider the linearization of this problem at this point. So the linearization, where I'm using this word very imprecisely, the linearization of my situation, of my problem, at my given point is, well, I take a derivative of both sides. On the left, I'll get, how do I want to say this? dg, the abstract derivative at my point y naught z naught of h. And on the right, I would just get 0. the zero mapping of H, which is the zero vector, because C is constant. Okay, phrasing this in terms of Jacobians, we would get the Jacobian G prime of y naught z naught times H equals 0. Now, writing this out a little bit more, the Jacobian, earlier we have this new notation G prime y and G prime z. Okay, after more technical difficulties, we're back. So what I was saying is the Jacobian here, earlier we introduced this new definition for the two different parts of the Jacobian. So I can write this matrix like this. And then similarly, H is a vector in R plus K. It sort of represents the linearized y and z variables. So what I can do is I can break this up into two components. I can write this as H sub y and H sub z, where H sub y is in RR. It represents all of the sort of linearized y variables, and likewise with z. So doing that gives me a vector like this. And I want this to be the zero vector. Okay, so we started out with this equation, this nonlinear equation that I want to solve for z. The linearized version of this problem at the point of interest is this equation. What we want to do now, roughly, is solve for the linearized z variables in terms of the linearized y variables. So the goal is now to solve for hz. Well, so this is a little goofy looking because this is like a matrix of matrices and a vector of vectors, but we can still treat this as a matrix vector product and just multiply this out. So if I do that, I'm going to get this guy times this. Plus this guy times this. Equals 0. But then we could just do some basic matrix algebra to solve for the linearized z variables. In particular, I'll just move this to the other side, and then again, by assumption, this is an invertible matrix. So I can just multiply through by the inverse to isolate this. So I'll do a bunch of that in one step, but if I do all of that, I can isolate h sub z as, well, I've moved this over here, then I multiplied on the left by the inverse of this matrix. That's going to give me negative g prime z at my point inverse times this stuff. Okay, and so the point here is that we have solved the linearized version of this problem. Therefore, I'll write down the general philosophy that I described at the beginning of the proof idea. So since we solved the linearized problem at the point of interest by this philosophy of calculus or whatever, locally we can solve the nonlinear problem. Done. So again, this is not a proof. This is just like the basic idea or something to maybe convince you why this would be true and how we explicitly use the fact that the G prime Z matrix is invertible. Okay. Now, this is the cool part. This is where we get to actually have some fun and do some examples, because so far, you know, I started out with this motivating circle example, and then since then I've just defined a ton of notation and talked about a bunch of abstract crazy stuff. And even just looking at this theorem is kind of horrifying. So what I want to do now is I want to look at a couple specific examples to put this in action, to tie all of this together so you can see down to earth what we're actually talking about. Like I said, this is the fun part. Okay, so first example. I'm going to give us an equation, just one good old equation with 3 variables. So consider the equation, what do I want to do? X times y minus z log of y plus e to the xz equals 1. And I'll just tell us that a particular solution is the point 0, 1, 1. So we can just check, right? This will be 0, 1, log of 1 is 0, so this is 0. So 1 equals 1. Okay, so that checks out. So the question that I want to ask is, can we solve for z as a function of x and y near this point? Let's check. So here's the point of all of this. This is a question I probably could have given you when you were like an Algebra 1 student or something like that. Give you some equation, and I ask you, can you do the algebra to solve for z in terms of x and y? If you want, you could just try, right? You have some equation, just do some algebra. The point is like, well, it looks kind of hard. There's a z here, there's a z here. You know, I'm pretty good at algebra, but I don't think I could solve this. I don't know what kind of tricks we could do. So this is exactly the point. Like, given an equation like this, it's hard, possibly impossible, to actually do the algebra to isolate one of the variables. This is where the implicit function theorem kicks in, and we can use the theorem to tell us if it's possible and to get a good approximation for the solution. But anyway, let's see if it's possible first. Okay, so to answer this question, rather, to use the implicit function theorem to answer the question, we need a function. G in this case is going to be, so I've got 3 variables in one equation. So this is kind of mimicking how I went about this, the first circle example. But I can define z by, or g rather, by g of x, y, z is this expression. Okay, the implicit function theorem says what you should do is you should first of all compute the Jacobian of this guy. So the whole Jacobian is going to be a 1 by 3 matrix. The first thing is the x derivative. So I'll get y plus z times e to the xz, I think. Second component's the y derivative. So I'll get x minus z over y. Then the third component is the z derivative. We'll get negative log y. Then let's see, plus, I'm taking a z derivative, so plus x times e to the xz. Okay, but I actually just care about the Jacobian at my specific point, right? So g prime of this point 0, 1, 1, this is going to be, let's see, 1 plus 1 is 2. 0 minus 1 is negative 1. And then here, this is going to be 0 plus 0. Okay, what is our g prime sub y and g prime sub z? We're using different variable names, but this, again, we have one equation, and I'm asking, can I solve for one variable in terms of the others? So this is going to be g prime of z at my point of interest. That's the thing that we want to know whether it's invertible. And then this is the other part. So maybe I'll say g prime x, y. Okay, well, g prime z, so 1 by 1 matrix. It's the 1 by 1 matrix, which is the number 0. This is not invertible. Therefore, no, we cannot locally solve for z as a function of x and y near this point. Okay, so that's kind of boring. We didn't really get to actually use the implicit function theorem, so instead I could ask a slightly different question, which is, what if, with the same equation and same solution, could you solve for y as a function of x and z? In this case, I want to do the exact same thing, but I'll rewrite the order of my variables to be consistent with how I talked about the implicit function theorem. So in this case, the kind of thing I would be interested in is the Jacobian of g with respect to x, z, y. I want to put the thing that I'm trying to isolate on the far right side. Well, this would be the matrix. It'll be the same matrix, right? But with the components changed, the z and the y components switched. So now I'm doing y last, and I'm doing z in the middle. So the Jacobian at the point we care about, which is still, 0, 1, 1, even though I've flipped the order of y and z, I'll get the matrix 2, 0, negative 1. Now this is now the matrix we care about. This is G prime Y of 0, 1, 1. And this is the other one, G prime X, Z. This matrix is invertible. It's a 1 by 1 matrix, -1. Its inverse is the number -1. -1 times -1 is 1, which is the 1 by 1 identity matrix. So this time, G prime sub Y is invertible. So since G prime sub Y at this point, which is, again, the 1 by 1 matrix -1, this is invertible. Yes, we can locally solve for Y in terms of X and Z near this point. In other words, there's some function out there. I don't know what I just wrote, i.e. In other words, there is some function phi defined, I'll be a little lazy, I'll say it this way. There is some function phi, and it's a function of X and Z. It's defined near the point 0, 1. And it gives us the Y values. In other words, there's some function phi which would be solving this equation for Y in terms of X and Z. And it looks like, oh, yeah, I still don't know how I do that. This would be pretty hard. So this is kind of the point. And again, we don't know what phi is. But this is where the moreover part of the implicit function theorem kicks in, and my remark after the theorem. We don't know what phi is. It exists. The implicit function theorem tells us that this is possible, but doesn't tell us what phi is. But we can get a degree 1 approximation of phi using this moreover statement. So I'm actually gonna, let me copy this so we can remember it. Because this is what I want to do next. So we don't know what phi is, but so we have phi of xz is approximately going to be, well, so we'll have to be a little careful with the variables here because we're using x, y, and z in terms of, instead of like the y1 to z1, whatever. So this number is like the output of phi at the point 0, 1, which is the y value. It's the number 1. Minus the inverse of the relevant G prime matrix, which is here. So this will be the inverse of the number -1. Let's see. Times this matrix, which is this guy, times this vector, which is going to be, in our case, x minus the x value, z minus the z value, which is 1. And if we simplify this, so the inverse of the matrix -1 is -1. You could think about this as being like 1 over -1. times, if you multiply this stuff out, you'll get 2 times x plus 0 times this, so plus 0. Okay, and so what do we get? Again, I find this really cool, and to me this is really satisfying, and it ties together all of the stuff that we've talked about so far. Here's what we've just shown. We found a particular solution of this equation, this random nonlinear equation, where the algebra, actually doing algebra here to solve for whatever variable we care about is impossible. We can't do it. But we found a particular solution. And the implicit function theorem tells us that near that solution, we can solve for y in terms of x and z. And we can't figure out exactly what that is explicitly, but up to degree 1, y is going to look like 1 plus 2x. That's so cool. Okay, let's do another example. And then I have a few comments about this afterwards. But I'll reiterate what we've done, because this is the whole point of the process. Nonlinear equation. We want to solve it for a variable. Can't. Implicit function theorem says that locally, if you can solve the linearized thing, or if you can solve the linearized thing at a point, then locally you can solve the problem. And we get a linear approximation for the solution. Cool stuff. Okay, one more example. Okay, so this time I want to consider a system of equations. I'm going to have 3 equations, and there are going to be 4 variables. So let's do xy squared minus xz plus wy equals 1. yw squared minus z equals 0. And wx plus yz plus w equals 3. Okay, so some ridiculous, again, nonlinear system of equations. And the question I want to ask is, or actually note that, so here's a particular solution, 1, 1, 1, 1. And again, we can check. 1 minus 1 plus 1 is 1. 1 minus 1 is 0. And it's 3. Okay, so it checks out. And the question is, can we solve for the 3 variables x, y, z in terms of the 4th variable? So now I have 3 variables, x, y, and z. This is going to act like my z vector in the statement of the implicit function theorem, confusingly. And then the variable that I want to solve in terms of is w. I'll reiterate again, if you want, you could just try doing the algebra. Maybe you can do it, but the squared and the w squared, it's like slightly nonlinear. In general, this looks kind of difficult. Oh, actually, this is highly nonlinear because these are all variables, right? Point is, you can play around with it, but actually doing the algebra, like if we were in high school, to solve for these variables is very difficult, probably impossible. So what do? Use the implicit function theorem. Okay, same thing as before. So what would this look like in this situation? Now I have 4 variables, 3 equations. So I would define g from R4 to R3 by so g of, let's do w, x, y, z. I'm going to do it in this order because, again, to be consistent with my statement of the theorem, I want to solve for these 3 variables in terms of this variable. And it's going to be the vector whose components are the corresponding components here. Yikes. So again, this is like G1, G2, G3. Okay. Well, what do? Implicit function theorem says figure out what the Jacobian is. So g prime of w, x, y, z. Okay, so R4 to R3, this is going to be a 3 by 4 matrix. The first row is going to be all the partial derivatives of this thing. So with respect to w first, we'll get y. With respect to x, we'll get y squared minus z. With respect to y, we'll get 2xy plus w. And with respect to z, we'll get negative x. Okay, now we do the same thing with the second row. So with respect to w, we'll get 2yw. With respect to x, we'll get 0. With respect to y, we'll get w squared and then negative 1. And then with the third row, we'll get, let's see, x plus 1. Right, x plus 1. W z y. Okay, so this is the Jacobian of g, the big Jacobian. In our case now, the thing that we care about being invertible, actually, sorry, let me write down the Jacobian at the point we care about. So at 1, 1, 1, 1, this will be 1, 0, 3, negative 1. 1, 0, 1, negative 1. 2, 1, 1, 1. Okay, that's the Jacobian we care about. The implicit function theorem in this case is going to tell us to consider this guy. Because these are the variables that we're trying to solve for. Okay, so now we're kind of a little out of scope of what we've talked about in class because I haven't really talked about, determinants or like how do we actually determine whether, say, a 3 by 3 matrix is invertible. So you have to trust me for now, but it turns out that yes, this is invertible. For example, if you know how to compute determinants, the determinant of the green thing, we could do a cofactor expansion argument along the first column. 0, 0 plus 1 times the determinant of this is going to be -3 plus 1, which is -2. So the determinant, if I did that right, is -2, which is not 0, so it is invertible. Okay, so if you believe me there, then the answer is yes. We can, according to the implicit function theorem, we can solve for x, y, z in terms of w. Yes, we can. Okay, so again, same situation as before. Like, the implicit function theorem tells us that in theory, yes, you can solve for x, y, z in terms of w. In other words, what this means is that there's going to be a function phi such that phi is going to be a function of w, and it will give us x as a function of w, y as a function of w, and z is a function of w. It doesn't tell us what phi is, but we can do the same thing that we did before and use the moreover part to get a degree 1 approximation to phi. So, moreover, phi of w will approximately be, well, it'll be phi of w naught, which is 1. So this is the vector 1, 1, 1. Minus the inverse of this matrix. So I will talk about that in a second, but for now I'll just write that times what? So let me scroll back up here. So I have the inverse of the relevant matrix times the other part of the Jacobian, which in our case here is going to be this. So that's 1, 1, 2. Times our linearized variables. So this will be like, oh, sorry. We only have one variable. So this is like w minus the w value, which is 1. Okay. Now, to simplify this out a little bit, again, in this class, if you're listening and you're actually in 32AH, we haven't talked about how to invert a matrix, but maybe some of you listening know how to do that, so you can try it. Or I'll just tell you that it turns out the inverse is 1/2 times, so I had Wolfram compute this for me earlier, -2, 4, 2, 1, -1, 0, 1, -3, 0. So how did I get this? Who knows? But if you want, you could just verify that if you take this times the green matrix, you'll get the identity, and vice versa. Okay, so let's simplify this out a little bit more. If I do this matrix vector product, I'm going to get -2 plus 4 plus 4. Actually, for the sake of time, you can multiply those stuff out. Let me just tell you what we get. If I did this correctly, we'll get 6 minus 5w 1/2 plus 1/2 w and negative 3/2 plus 5/2 w. So x, y, z is approximately that near our solution. Okay, I'm going to say this again. Again, I find this really cool. What we've done is we were given this highly nonlinear algebraic system of equations that we probably can't solve using actual algebra. But I found one solution, and then using the implicit function theorem, we can determine whether, like, yes or no, it is theoretically possible to solve for x, y, z in terms of w, and we can get an approximation for the solution. This is so cool. Okay, what I want to do is I want to finish with some more geometric remarks about what we've done here and about what these past two examples show. So, maybe let me do this. I want to go back to this first example. Something in particular about this one, something about this should feel really familiar. Here's what we've done. This equation defines a surface, right? We've thought about this kind of thing before, is that if you have one equation involving 3 variables, that's going to cut out a surface. The heuristic here is that if you have 3 variables and one equation, geometrically, this describes a 3 minus 1, which is 2-dimensional blob. So whatever dimension means, this one equation in 3 variables describes a 2-dimensional blob, which is a surface. This is the equation of the tangent plane to that surface at the point of interest. So this should make a whole lot of sense, right? What we're doing here is we have some surface, and I've found a point. Maybe I'll draw a picture. We have some surface and some point, and what we've done is we've computed the tangent plane at that point. The idea being, if that tangent plane looks like the graph of a function x and z, then locally the blob, the 2-dimensional thing cut out by our equation, will look like the graph of a function of x and z. Likewise, in the second example, let's think about what we've done here. This time we had 4 variables, 3 equations. 4 variables, 3 equations. This is going to describe a 1-dimensional blob in R4. In other words, this system of equations cuts out a curve, some curve in 4 dimensions. Basically, what we've asked here is, can I parameterize this curve using W locally? Near my, on a certain point of the curve, can I locally parameterize the curve using W? And it turns out that the answer is yes. This is what we showed. So I'm actually going to write this down, maybe. Remark. What we've shown is that locally we can parameterize the curve cut out by g of w, x, y, z equals that constant vector. using W. Specifically, we would get a parameterization, a local parameterization, by saying, well, W is W, it's the parameter, and then X is whatever whatever this is. Y is whatever this is, Z is whatever this is. So again, this is a geometric way to think about what we're doing here. Furthermore, what this linear approximation basically describes is the tangent line to that curve at this point. So the tangent line at the point 1, 1, 1, 1 is parameterized by right. So what this shows is that locally we can parameterize the curve using W, and this describes the tangent line to the curve. So the tangent line is parameterized by I'll just be a little lazy and I'll say, well, W is W, and then here are X, Y, and Z. So this expression here, this best approximation to the function phi, you can think about this basically as describing the tangent line to the curve. In complete analogy with the other example where I talked about the best approximation function is basically describing the tangent plane. So again, all of this makes sense. Everything's tied together, and in this sense you can think about this implicit function theorem stuff as sort of being a generalization for finding tangent objects to given geometric things cut out by systems of equations. Anyway, implicit function theorem's great. Not only is it really important and interesting just in its own right, but we've seen how it's important for thinking about solving systems of equations like this, but it turns out it's extremely important for a number of other reasons. For our purposes, what we will soon see, depending on when you watch this video, the method of Lagrange multipliers follows from the implicit function theorem. So optimization is a huge application of the implicit function theorem. And then from my personal perspective, a whole lot of differential geometry, studying manifolds and stuff like that, relies on statements like the implicit function theorem. I won't talk about that now, but turns out it's really important. This video is super long already, so I'm going to call it quits here. At the end of a real lecture, I would ask if there are any questions, but I'm talking to myself. So with that, goodbye.